Hello everyone, this is Dr. Hopkins with our next video, and this isn't about buffers anymore. We are now talking about titration curves, and actually this is going to be the last topic in our exploration of acid-base chemistry here in 106. So just a kind of a review of what we know about titration. So this idea of a titration we understand, at least we did it in lab last semester. You added a titrant, and if we're talking about acid-base, which we are, that titrant is either the acid or the base, and it's added to the opposite to measure a particular property. And in the first semester, that particular property was the concentration of what we were titrating, what you put in the Erlenmeyer flask, if you will. The equivalence point, just to remember, the moles of titrant was equal to the moles of the titrated component, so moles of acid equals moles of base at the equivalence point. The endpoint was the moles of titrant that triggered the indicator, and of course, if you had a well-designed titration, your endpoint and your equivalence point should be very similar. So, for example, the indicator was your phenolphthalein turning from clear to a pink or almost purple color, right? And in that case, we were doing kind of single output or single data titrations, but we can also use a titration to measure a range of properties. So if we have a component, an acid or a base in our Erlenmeyer flask, the titrant or the titrated component, we can add titrant and see how, say, the pH changes now that we've been discussing pH. So what you'll get in that case is what we call a pH titration curve, or an acid-base titration curve. And basically it's just the plot of the property. So it's plot of pH versus titrant added is any kind of titration curve. And we could do a titration curve for redox reactions. It doesn't really matter, but we happen to be talking about acid-base reactions. So here I show an example of a titration curve where you have pH on the y-axis, milliliters, in this case of sodium hydroxide, on the x-axis, given, and you can see at the beginning of the titration curve we're in the range where we have excess moles of acid, and then you'll notice it goes up sharply, the pH goes up sharply around 25, and in the middle of this rise, so you'll see this is kind of common to acid-base titration curves, is the equivalence point, so this kind of sharp rise in pH, and then beyond that we're in excess base. Okay, so we'll use that inflection to determine the equivalence point. So we could use this without even using an indicator. We could do a titration curve to determine our equivalence point. All right, so let's do this. Now the idea of a titration curve in lab is actually quite simple. You just make up your whatever you're going to titrate, put a pH meter in there and add acid or base, figure out the pH versus milliliters added, plot it, and you have your titration curve. And as the same with buffers, in class, it's a little bit more complicated, but it's nothing we cannot do. Actually, as a matter of fact, this is really a review of everything we've learned in terms of reactivity for Bronsted-Lowry acids and bases. So what we're going to do is we're going to take 25 milliliters of 0.1 molar HCl. That's going to be our titrated component. And we're going to put 0.1 molar sodium hydroxide in a burette, and we're going to start titrating. We're going to determine in class calculating what the pH is at 0, 10, 25, and 30. Of course, 0 is before you start titrating. All right, so now we have our problem set up. We have 25 milliliters of our 0.1 molar HCl, and we're going to add 0.1 molar sodium hydroxide to it by a certain number of milliliters. So we had 4 different ones, and I've got A written here, so we add 0 milliliters. This is before we add any sodium hydroxide. All we have at that point is HCl, so we don't really need to figure out moles because we know the pH is just the negative log of the H plus concentration, which is the negative log of 0.1 because it's 0.1 molar, and that's equal to 1.0. So the pH before we started is a pH of 1.0, which HCl makes sense. All right, so now let's add 10 milliliters of 0.1 molar sodium hydroxide and figure out what happens. Well, if we do that, we need to start, we're going to do a reaction because we've just added a strong base to a strong acid. And so I've gone ahead and calculated the moles. So this is the moles of the acid, the H plus, because that's our concentration of HCl in our milliliters. And then we added 10 milliliters, and I converted it from 10 milliliters to 0.01 liters times 0.1 molar, and we get 1 times 10 to the minus 3. So that's our OH minus. So now we're going to write our reaction. I'm going to write it in kind of shorthand here, where we have H2O. And so then we just need to figure out what's limiting. I'm going to go ahead and do kind of the way we've been doing this all along. So the OH minus is limiting. We still have an excess of acid, but we need to figure out how many moles excess, and that's 1.5 times 10 to the minus 3. All right, and now in order to get our concentration of H plus, then is 1.5 times 10 to the minus 3 moles, and we need to divide that by liters. We're going to go ahead and add 0.025 to 0.01, or 25 plus 10 milliliters, and just assume it's 35. 0.035 liters, okay, is our concentration. And if we plug that in to the negative log of that number, I'm not going to calculate that number itself, and so our pH is equal to 1.37. So we added 10 milliliters of 0.1 molar sodium hydroxide, and we went from a pH of 1 to 1.37. So it's gone up a little bit. Now here we have part C, where we're adding 25 milliliters of 0.1 molar sodium hydroxide. I've got the moles of H plus because it's constant, was what we originally added. And now we've added, and we're going to convert this 25 milliliters to moles, and it's 2.5 times 10 to the minus 3, which is the same as 2.5 times 10 to the minus 3 here. That means we're not going to have, so we have stoichiometrically equivalent, which is the equivalence point, isn't it? And in this case, we have no excess H plus, we have no OH minus. What we're left with is water and our pH of pure water. We're not going to do the KW reaction because we already know it, but if we just have pure water and we let it auto-dissociate, we get a pH of 7. So once we get to 25, we're at the equivalence point, and we've gotten rid of all of our acid. Now the next step is adding 30 milliliters. So now we're gone past the equivalence point, and I've started from the reaction. So we're back to the reaction at this point because we're past the equivalence point. We got 30.1 as 3 times 10 to the minus 3 moles of OH minus, which I've put here. Now our limiting reactant is our H plus. So we're going to be left with 0 of that. And our our excess reactant is OH minus, and we're left with that number of moles. If I wanted to convert that to concentration, I need to divide it by the volume. In this case, let's assume that we have 0.055 liters, so 30 plus 25, right? 30 plus 25 milliliters equals 55 milliliters, right? And so then that's our concentration, which, if I'm not mistaken, is 9.1 times 10 to the minus 3. If we want to convert to pH, it's going to be 14 minus the minus log, so 14 minus the POH, which is 9.1 times 10 to the minus 3, and that is going to be 11.96. So we have a higher pH. Notice we went from pH 7, now we're really high, up to close to 12, because we have excess strong base. So here we have the sum of all of our four pH calculations for the four titration points, 0, 10, 25, 30. We had a pH of 1, 1.37, 7, 11.96. And so a titration curve would just be, now I'm hand drawing this, but clearly you would plot this in Excel or some other kind of plotting program. And we only have 4 of these. So if we wanted to, you could even draw this as a line, but really we know that we would get more of these, and eventually it would go up and look kind of like the titration curve shown earlier. So what we're going to do is we're going to calculate these and plot more milliliters added versus pH in class to make our titration curve. And finally, we have what we've learned from this video. So pH curves, pH titration curves are just basically a plot of pH on the y-axis versus milliliters of titrant. We can use them to determine the equivalence point, so we don't need an indicator. We can just do titration curves. And we can calculate every point on the curve because we know how to do all of the reaction and then conversion to pH. So until next time.